Now, at this point, we will define the concept of Cartesian product. And to do that, we have to first define the concept of an ordered pair. An ordered pair is an object of the form AB. So it's essentially a pair consisting of two elements. But as the name implies, the order is important. Okay, so the ordered pair AB is different than the ordered pair BA whenever A and B are different. Okay, so the ordered pair, we have a pair such that the order you put the ordered pair in is important. Now, the Cartesian product of two sets are set of ordered pairs where you take the first element from the first set here, and you take the second element of the ordered pair from the second element, so a second set. And all possible such ordered pairs should be included in the Cartesian product. So this is defined as the set of ordered pairs AB, where A is an element in A and B, this element B, is an element of set B. Now, simply let's look at this example. Let's say set A is 1, 2, set B is 1, 3, set C is the interval, the half-open interval from 1 to 3, where 1 is included, 3 is excluded. Set D is 2, 3, 4, and set E is again the half-open interval from 2 excluded up to 3 included. Now, the Cartesian product of AB and BA are given here. These are simple. You just take the first element from A and the second from B for this Cartesian product, and for this one, you take the first element from B, the second from A. It gets a little bit trickier when intervals are involved. For instance, the Cartesian product of C and D. D is a set with just 3 elements, 2, 3, 4, 2, 3, 4 here. But C is a half-open interval from 1 to 3. And you see, I have mapped the Cartesian product of C and D here in this graph. As element 1 is included in C, it's going to be included in the ordered pairs, but 3 is not an element of C, so it's not going to be included in the ordered pairs, and all the points in between will define the ordered pairs here. And the Cartesian product of C and D, now both of them are intervals, and so we get a region in the two-dimensional plane from this Cartesian product of each of these ordered pairs. But you need to be careful about which portions to include at the extremes. So C, remember, is the half-open interval from 1 to 3, but 1 is included, 3 is excluded. So this line here is solid, and this is included here, and 3 here is excluded. So this line is dashed. It's not included in the Cartesian product. And E, again, is a half-open interval. 2 is excluded, 3 is included. So here, this line here is excluded, but this line included. You see, this is an empty point. It's not included in the Cartesian product because number 3 is not included in C. 3 is included in E, but it's not included in C. So the ordered pair 3, 3 is not in C times E. Of course, we can generalize ordered pairs to ordered n tuples, right? If you have n sets having a Cartesian product, you can define this as the set of n tuples, of course, the set of ordered n tuples, and the order here is important, where each of these components are taken from each of these sets in the specific order. Let's look at the properties of the Cartesian product. First of all, since the order is important in an ordered pair, A times B in general is different than B times A. You have to switch the order of ordered pairs to obtain one from the other. And it's associative. A times B times C is equal to A times B times C. But here you see, this here is a set of ordered pairs. So when you take the Cartesian product of A with B times C, what you get is ordered pairs where the second element is also an ordered pair of this form. And when you look at this one, the first set is itself a Cartesian product, so it includes ordered pairs. And the second one, C, is an ordinary set. We don't know what elements it has. Therefore, the elements of this Cartesian product are of the form, well, you have an ordered pair, but the first element is also an ordered pair in this form. Here we assume that both of these representations are equivalent, and essentially they form an ordered triplet. If you make this interpretation, then Cartesian product becomes associative. And then Cartesian product of B intersection with C is equal to this one, which means Cartesian product distributes over intersection. And in the next one, we see that Cartesian product also distributes over union. I'm not going to prove this, not really that difficult. You can attempt yourself. And if you have A subset of C, as well as B a subset of D, in this case, we get the Cartesian product of A and C is a subset of B, Cartesian product B and D. And an immediate result of this property is that if A is a subset of B, then A times A is a subset of A times B, and also A times B is a subset of B times B. Or I can simply write this as A times A subset A times B subset B times B. Okay, finally, about the cardinality. The cardinality of the Cartesian product of A and B is equal to the product of their individual cardinalities.